For our first speaker in the afternoon session, we are very fortunate to have Professor Saurabh Gupta. Saurabh is an assistant professor in the EC department at UIUC. He received his PhD from UC Berkeley in 2018, and then he worked as a research scientist at Facebook AI Research. His research interests span computer vision, robotics, and machine learning, with a focus on building agents that can intelligently interact with the physical world around them. He has received numerous awards and challenges, including the President's Gold Medal at IIT Delhi and Google Fellowship and Amazon Research Award. Today, Saurabh is going to tell us about his work on learning to move and moving to learn. Without further delay, Saurabh, please take it away.
Yeah, thanks a lot, Quan, for that very kind introduction. And I'm very excited to be here to present some of my work. Thanks a lot for inviting me, and thanks a lot for everyone to come for coming. I'm in my talk today, I will basically be talking about navigating agents. So let's assume we have a robot which is equipped with a first-person camera, and we have dropped it into a novel environment that this robot has not been in before, right? And in this two-part talk, in the first part, I'll focus on learning to move, wherein I'll describe how we can get this agent that is being put in this environment for the first time, how we can get this agent to intelligently move around and do tasks. And the tasks that I'll be interested in are semantic exploration tasks, right? So these will be tasks of the form find objects of interest, right? So that's going to be the first part of my talk. And in the second part of my talk, I'll basically focus on moving to learn, where I'll talk about if agents can actually move around in their surroundings, in their environments, then how can that movement actually allow agents to improve their perception models through self-supervised interaction. So that's kind of what I'll try to do in this talk. Right? Okay, so let's get started. Let me first tell you about how we can train agents for learning to move. Now, I think as roboticists, I think we should basically be very, very careful when we are saying that we are going to learn something and to do something, right? Because after all, like this navigation problem has been around, I mean, it's been well studied over the last 5 decades, and you have systems which can do quite a lot already. So why is it that we think that learning should be able to help us to do something which we can't quite do, right? And I think this goes back to what Andy Davidson was also saying in the morning, right? That classical techniques in structure for motion and so forth have stood the test of time in terms of how well they do in context of learning and such, right? So I think whenever you hear learning in context of some robotic task, it's always necessary to, in my view, to critically analyze what is the role that learning will play in this particular task, right? And so I think that's how I'll start. Why is there the need for learning when we're trying to move, right? After all, we have classical methods which can do mapping and planning, and you can do quite well, right? So in my view, I think the role of learning in this context is in terms of speculating about what you don't directly observe, and thereby gaining efficiency in your behavior. So I'll give you 2 examples. So the first example is free space behind obstacles, right? You might be seeing this particular bathroom for the first time, but you have experience with a lot of other bathrooms, a lot of other hotel rooms in your past life, and that allows you to make speculations about what you're not directly observing, right? So you'll agree with me that if you wanted to exit this particular bathroom, you'll very likely take a trajectory which goes out and turns left, right? I mean, you're not seeing free space behind the doorway on the left-hand side, but you can speculate very well that that exists, and you can use that in terms of planning your actions for doing whatever you have to do. So I think that's kind of one aspect in which I believe learning is useful and can help. There's another aspect where I believe learning is useful, which is essentially leveraging semantic regularities, right? So here is another example. Here's an image of you are going to visit your friend for the first time, and this is where you are, and now you're looking for a couch, right? Now, again, you may not have been in this particular house for the first time. You may not have been in this particular house ever, but you've been in enough other houses that you realize that if you're looking for a couch, you're very likely going to go straight and turn to the right. And I mean, you're seeing this television. Maybe there's going to be a couch behind facing this television and so forth. Right? Now, this is again some sort of regularity that exists in real world environments that allows us to speculate about what we are not directly observing right now. And in my view, I think when we are trying to introduce learning into these architectures and so forth, one role for learning to play is how we can make speculations of this form. And in my talk today, I'll basically try to share with you how we can do that. Right? Okay. Now, I think, okay, so if you're on board with me that there is some role for learning to play, question is how can we incorporate, how can we leverage this, the benefits of learning in policies that can navigate, right? Now, if you, so the popular paradigm for incorporating this kind of reasoning in modern times is essentially use of end-to-end reinforcement learning, right? So we cast navigation as a policy learning problem, and we then basically involve lots and lots of reinforcement learning. We build a simulator. And now, you use reinforcement learning for learning these things. Now, if you're using reinforcement learning as a tool, then it will actually pick up on these kind of cues that I'm talking about, right? So if you're training a policy, the policy over the course of training will realize that there are some statistical regularities in the underlying world that I should be leveraging in order to move around, right? So that's what these things are learning. But at the same time, once you cast this problem as a purely learning problem, you are faced with the challenges that come along with it, right? In particular, for reinforcement learning, it's very clear we need many, many millions of samples, sometimes billions of samples for training anything, right? And so that basically means you cannot really train in the real world. You have to build a simulator. Now, building a simulator is hard. You have to pay designers to do it, or you have to do something else, right? So at the end of the day, maybe you train this policy in simulation, but then you're faced with this sim to real problem that, how do you get these policies to work in the real world and so forth, right? Now, I think the question that I want you to think about today is there an alternate way of reaping the benefits of learning for the kind of things that I talked about? And I think this point was also made by an earlier speaker, Gupta. He also basically said the same thing, which is reinforcement learning and training in simulation the only way of reaping the benefits of learning? And I think that's kind of also the question that I'm going to be revisiting. And my answer is going to be, actually, it turns out to be similar to what Abhinav's answer was, that yes, we can get quite far simply by watching egocentric videos of people walking around in their environment. And that's what I'm going to tell you about today, right? So the kind of videos that I'm going to be referring to is these videos that people upload to YouTube. These videos are real estate videos, and there's a reason why people readily upload them to YouTube, which is that they may want to sell or rent out their apartment or their house, right? So, it's better than putting pictures on pictures. If you have a video, people get a much better sense of why you want to, you may want to buy this or not, right? Especially in current times. Okay, so these are the videos I'm going to be talking about. And it turns out, as I said, it's not just one video. There are actually lots and lots of such videos. And in fact, in our work, we collected a data set where we were able to crawl 1,500 such videos. And that's kind of what we are going to be trying to see how we can use them for any kind of learning, right? Okay, so this is what is the data that we're going to work with. Now, I think intuitively, first, I'd like to convey to you how or what can these videos tell us about navigation. And I'll go back to exactly the two things that we started this talk with. I think these videos actually show us where can we go from here and how, right? So again, this particular picture that you saw, this is a video actually. And now if you follow this video along, you can actually infer that from this particular starting location, there is a feasible trajectory that goes out of the room and turns left, right? So we are seeing that behavior explicitly. And if we can somehow use somehow design learning techniques which can help us mine this signal, then we'll basically be able to incorporate this kind of speculative reasoning in policies that we're learning. These videos also tell us what is next to what, right? So again, this if you have been in lots of other houses before, and in, let's say, in some other house, you saw this kind of a trajectory where you walk into the entrance and then you turn around and now you see a couch, right? Now, if you see this trajectory, in this video, this will allow you to make this inference that from the first image, if I were looking for a couch, then basically there's a couch around the corner and I can find it, right? So, we have been working with this insight for quite some time, and we have been developing techniques for doing this. In today's talk, I'll first focus on what is next to what, and I'll show you how we can build this kind of speculative reasoning about where are objects in scenes. If time permits, I'll also talk about the former, which is how can you infer, where can you go from here and how, but we'll see if time permits. Right? Okay, so this is some work that we presented at NeurIPS last year in 2020. It's called Semantic Visual Navigation by Watching YouTube Videos. And this was work that was led by my students, Matthew Chang and Arjun Gupta. Okay, so we have these videos. Now we want to do some learning on top of these, right? Now it turns out there are some challenges that come about when you start thinking about how can you use these videos for learning, right? So the first challenge is they don't come with any kind of action labels, right? You don't quite know what is the action that the person who is shooting this video executed, right? We don't have action labels. Now, second aspect is goals and intents in these videos are not known. I don't know what is this person going to show me, right? I mean, they're going to show me their house, but I don't quite know what are they going to show me first. I don't know what they will be doing in the future. A third aspect in which challenging is difficult from these videos is that depicted trajectories may not be optimal, right? I don't know what this person is interested in doing. I mean, this person took a detour and showed me this bathroom, but that's kind of not optimal if I wanted to find a staircase and go up the stairs and so forth. Okay? So there are challenges in using these kind of videos. And what we have done is we have worked out how we can circumvent these challenges and still arrive at, still extract some learning signal from this, right? So the first thing, the first problem that we had, which is that these videos don't come with action labels. We are solving that by doing action grounding by training an inverse model. And I'll say more about that in just a second. The second aspect, which is goals and intents are not known. We are going to be using an off-the-shelf object detector that can label us with frames that have the desired object of interest, right? So again, remember the task is I want to find, for example, a chair or a bathroom, or going back to Abhinav's talk, I'm trying to find a toilet seat or whatever, right? So I have object detectors for these and I will run those. And that's kind of where my, in some sense, reward signal is going to come from. And the last aspect, which is that depicted trajectories may not be optimal. We are going to use Q learning and that can generate optimal behavior from suboptimal data. Right? So let me give you a little bit more detail about what we are going to be doing. So this action grounding by inverse models happens in the following way. So we have a robot, and we can basically have this robot execute random actions in the environment. This will give us a trajectory, IT, which is the current image, AT, the action this robot took, and IT plus 1, the next image that the robot is observed. Now, from this data, we can actually train an inverse model, where this inverse model takes IT and IT plus 1 as input, and it tries to output what action did the robot execute in going from image IT to IT plus 1, right? Now, this is a standard supervised learning model that we can train. You have IT, you have IT plus 1, you have AT plus 1, and so forth. Now, crucially, I think this model doesn't require too much data for training. The reason is it only needs to reason very, very locally. You only, given a pair of images, you're just trying to roughly predict, did the robot go straight? Did the robot turn left? Did the robot turn right? Which, I mean, we are in this case, for generality's sake, we are learning an inverse model, which is a more general way of thinking about this. But for this specific navigation problem, you could actually alternatively also do structure from motion, right? You could basically do structure from motion on short trajectories, and that will give you some sort of action grounding. Did the robot turn left? Did the robot turn right? Or did it go straight? But like a more general version of this is you can actually train an inverse model. It takes a little bit of samples for training this. And in our experience, it worked reasonably well in grounding these videos with actions. The second aspect, which if you're not familiar with, is Q learning. Again, I won't quite go into all the details, but there's a paper, the reference that you can see. And the nice thing about Q learning is that it can learn from off-policy data. So even if I don't have any optimal data, Q learning can, given transition quadruples of the form S, A, S prime R, Q learning will allow me to recover the optimal value, optimal Q function. I mean, modulo some conditions, some technical conditions on coverage and so forth. And that's kind of a neat result from back in the day. And this is what we're going to do, right? And again, I believe audience must be familiar with this, so I won't quite go into all of the things. Maybe one thing I'll mention is that, just to set notation, right? Q star of S comma A is essentially measuring the return of an optimal policy when executing action A from state S, right? And in some sense, you can interpret this as how close you are to the goal after you have executed action. That's what Q star of S comma A is going to be measured. Okay, good. So this basically leads us to our framework, which we are calling value learning from videos. And it starts from these real estate tours from YouTube. Here is this the video snippet. And now the first step, as I said, is action grounding. We are going to say what action did the agent take in order to go from IT-1 to IT+1. And then we are going to do goal labeling, which is we are going to run an object detector that has been trained on internet data. So Microsoft Coco data set or whatever you have. And this detector predicts what objects you can see right now. Now, with this information, now we can actually construct data for doing Q-learning. We basically needed IT, AT, IT+1, and reward. These are the 4 things that I needed, and I can compute all of those 4 things using this inverse model and this object detector that I have. And this basically gives me a Q-learning quadruple, which I'm going to do Q-learning with. It will give me a Q function, which, given the current image and the action that the robot wants to take right now, and again, in this case, C is the object class that this agent is looking for. I get this Q function. I'm going to take a max over A, and that's going to give me this function Fi, C, which is a value function that uses implicitly learns semantic cues for seeking objects in novel environments. Right. So let me show you intuitively what this value function has learned. So this value function, as I said, is going to measure some form of nearness to goal. And this is like an image that we are running this value function on. And here is the prediction for what it says, right? So again, higher is better, nearness to goal. So high means you are close to goal. And on the bottom here, I'm showing you the values that have been predicted in the different directions for these different categories: chairs, couches, dining tables, bed, and toilets, right? Now, a few things to notice. So this value function, I mean, you can see some chairs, you can see some couch, you can kind of see some dining table back over here. It has high values in this direction where you're actually already seeing the object, right? So it seems to be doing something reasonable, something that would make sense. But I think more interesting aspect is that this value function actually is able to incorporate a speculative power that you're not really seeing a bed anywhere in this panorama, in this image, but it is essentially having a high value into this hallway, building in the speculation that beds, I mean, that there's kind of an apartment. If you go down a hallway, you're very likely going to see a bedroom, and that's kind of why the value is high. Right? You can actually look at it another way. You can look at it in kind of a top view kind of a thing. I mean, here is a dining table. This is a value function for where it thinks the dining table is. And the value function essentially learns to predict like a proxy for nearness that we are interested in. Right? Okay, good. So I think what we have done is essentially we have learned these value functions. And now question is, how do we use these value functions for doing semantic navigation, right? And for this, we are building on some of our past work where we designed hierarchical policies. And this hierarchical policy has a high-level policy which decides where to go, and it emits a short-term goal. And this short-term goal is consumed by a low-level policy, which executes actions to achieve the short-term goal, right? So we are doing this in a topological fashion because you get robustness to errors and all of that. And this topological graph, I mean, has nodes which correspond to past locations that the agent has been at. And it is building expectations as to where all it can go. And if it were to go in that particular direction, how likely is it for it to find the object that we're interested in, right? So this is essentially the values that I showed you on the previous 2 slides. For each node, you have a panorama, and it basically gives you that, okay, this is how likely it is to find this object in this particular direction. So this is kind of the representation that we're building as we're going along. And now basically you select the most promising direction, you sample a point in that direction, and you say, okay, I want my robot to go some distance in that particular direction. And this is passed on to this low-level policy, which essentially is going to execute this action based on a depth sensor. So we are actually using a RGBD camera over here. It basically incrementally builds a local occupancy map. And you basically have a small, you are building a map, you have a nearby point that you want to go to, and you can use classical path planning in order to do this. We are using fast marching method to do this. And basically this generates an action, you execute that action, and once you get close enough, you basically return control to the high level policy, right? Okay, yeah. And again, I think, I mean, just to set things in context, what we did was we borrowed architectures from classical robotics, which we know work, which have a lot of desirable things. Path planning is a very desirable thing. It gives you a lot of reasoning and all of that. We took those, and what we did was we introduced learning where it was necessary in order to get systems to work better than what they did in the past. Okay, okay. So here are some experimental results. On the x-axis, I'm plotting number of frames that were used for training. And on the y-axis, I'm plotting some measure of how quickly can you find objects in the scene, right? So higher is better, and you basically want to use as few frames for training as you would like, right? So in red, basically you have our method, which is trained on YouTube videos, and we are testing in this habitat simulator. So we are, in some sense, our method is suffering from real to sim gap. Our method was trained in the real world, but we are testing it in simulation, right? So our method is being penalized unnecessarily. But it turns out that we are actually still able to outperform a number of these learning-based methods quite impressively, right? So what I'm showing here is a comparison to RL-based methods, which is, again, don't work really as well. And even after 35 million frames of training, you don't get very good performance, whereas with our method, you get quite good performance, right? We have some other comparisons also to strong exploration baselines, which it actually turns out do quite well over here. And this is again, right, so this is basically this particular dot where we are essentially systematically exploring the environment. And once we see an object, we go towards it, right? So it's not quite doing anything very sophisticated. It's a baseline you can build out of classical methods. And it turns out that actually does better than a number of these RL-based methods, right? And that's, I think, going back to the early part of my talk, I think that's kind of the reason why I said we should carefully think if we are jumping on the learning bandwagon, then we should figure out what is the contribution of learning and how is it advancing the state of the art beyond what we already know. Right? Okay, I think these were kind of results on this object code task. We have some ablations, which I guess in the interest of time, I will not quite go into. I mean, turns out, whatever detectors we are using, etc., don't really matter. You still get good performance. I guess the one highlight that I like to point out is that if we did not use a hierarchical architecture, but if we just use the queue function as is, performance is much worse, right? So just using the queue function is not very good. This hierarchy allows you to does quite a bit of the heavy lifting. I guess another thing that might be of interest is that queue learning allows us to compose, find optimal trajectories, right? So if you did not do queue learning, if you just did policy evaluation, you'll get value functions which will mislead you because they will follow the policy that the agent took rather than the optimal policy. So queue learning is useful, and you can construct environments in which that effect can be seen. Okay, here is a video which shows navigation to novel objects. Yeah, so in this case, we're looking for a couch. Yeah, so it's going to be doing this. And again, I think we are training our networks on real data, but we are testing on whatever simulation environments that are available for doing systematic evaluations. And that's kind of the artifacts that you're seeing here. Okay, good. So I think that's kind of what I wanted to talk about in terms of what is next to what, how you can learn this by essentially just watching videos. I don't think I have the time to actually talk about where you can go from here and how, but this is some work that's actually some older work which we presented at Coral 2019, where again, the story is the same. We want to learn by just watching videos, how can agents build speculative models of what is around them, and how can they do it. And I won't go into this paper, but here is a pointer to this paper, and I encourage you to take a look at this. I mean, because this is RSS, I guess I should point out that we have a paper which is actually employing some of the same techniques, some of the same principles of identifying and injecting learning where necessary. And this is in some outdoor settings where we are able to learn policies for driving in crop rows using a learning plus RGB camera system, and it outperforms a LiDAR-based system on a number of different settings. And we double the amount of distance you travel without interventions, at the same time lowering cost by quite some time, right? So this is again another example where thinking about where is learning important and how you can efficiently incorporate it into algorithms gets us quite a bit, right? Again, there was no end-to-end RL here. There was pure supervised learning, and it works quite well. I encourage you to check this paper out. Okay. I guess I'm quite a bit short of time. I'll very quickly try to summarize some of our work on moving to learn, where essentially we are once we have agents that can actually navigate in environments, they can actually use self-supervision to improve their perception models, right? And again, this will be reasonably brief. But the problem is there's a robot, it's trying to detect chairs. It sees a chair in the far, it's not quite sure whether this is a chair or not. If this were an image on the internet, you can't do anything short of asking a human for this label. But if this is a robot that can actually interact with the world, it can walk up to the chair, and once it is close enough, at some point, maybe its chair detector will start firing, and now it can go back and relabel the data that it saw earlier and try to improve its model, right? So this is the basic idea, and basically there are questions of how do you seek data that provides opportunity for such learning, and how do we improve models based on the data that we have acquired? And these are the two questions that we tried to answer in this recent work that was led by Devendra Chaplot and Murtaza Dalal at CMU. And our answers to these two questions are, how do you seek data that provides opportunity for learning? You do gainful curiosity. You explicitly find, I'll talk a little bit about that. And how do we improve our models based on this data? You do label propagation in 3D semantic maps, right? So here is a 3D semantic map. I guess you have RGBD images, they come together and you basically do SLAM or whatever you want, and you build a semantic map based on detections that are coming from off-the-shelf trained mask RCNN detector, right? So this mask RCNN has been trained on internet data, and we're just using that to build a map and labeling the map, right? Now, once you have this map, you can basically do, so this is a visualization of this map being built over time. You're walking around, you're building this map. Wherever you have mask RCNN detections, you can label that in the point cloud and so forth, right? Now, once you have built this map, now you can start doing interesting things with this in the form that you can actually train a policy to encourage trajectories where you can actually learn something. So if you can label each voxel with a semantic predictor which has high score, then that is useful for generating data, right? So this is this notion of gainful curiosity. This is a self-supervised loss. You can train this automatically without needing any manual supervision and so forth. And this gives you a policy for exploration. And 3D label propagation also uses the same 3D semantic map. What we're doing is we take an RGB image and we render out the labels from this 3D semantic map that we have built up, right? And this can generate cleaner labels for you than what you had to begin with, right? So mask RCNN pre-trained has false positives. If you do this label smoothing in these 3D maps that we are building, you can actually do clean up false positives. You can actually also clean up recover from false positives and false negatives, right? So that's kind of what we're doing. And again, I think I won't quite go into the other details, but basically what this ends up allowing us is it allows us to do active learning, where we can take a set of training environments and we can do this self-supervised process on top of that. And I can basically improve my object detector, right? So I started with a pre-trained mask RCNN detector. It worked at 34.8 mean average precision. And by doing this active self-supervision in training environments, I'm able to improve this detector by 5.2% mean average precision. I can actually also do the same thing at test time, that I can use my curiosity policy and do some more retraining, and that actually gives me a little bit more improvement. Okay, I think that's all that I had for today. In summary, what I presented today was learning to move and moving to learn. When I spoke about learning to move, it was about using egocentric videos to learn policies for navigation. And when I talked about moving to learn, I presented this, I gave you a teaser for this framework where we are doing self-supervised embodied active learning. Here are the papers, here are the students who led all of this work, and I want to thank you for your attention. Happy to take any questions.
Thank you, Saurabh, for the great talk. If anyone has a question, feel free to directly raise your hand or post it in the chat. So one question that I have is, when you have this proxy for nearest, I wonder like what is the specific like definition of it? Like when for example, when the score reaches to 1, what does it mean? Does it mean like the object category is reachable in a few steps or anything like that?
Yeah, that's actually it falls out from. So we are doing Q learning with sparse rewards, you can say, right? So the images which are at the goal location have a reward of 1. All other steps have a reward of 0. So the value is essentially gamma to the power number of steps to goal, right? So the value basically, yeah, if you, gamma is a discount factor, and you can now compute, it roughly captures how many steps are there to the goal.
Got it. Yeah, that makes a lot of sense. Yeah, I guess given the time, we'll move on to the next speaker, and let's thank Saurabh again for the great talk. And Saurabh will come back in at 4 p.m. with other invited speakers to join the panel discussions. And we'll see you later, Saurabh.
Thanks a lot. Thanks for your time.